Okay, so let's get started. So you guys might have already seen this in the pre-lecture assignment videos, but I'm going to go over this very briefly. So you guys all know the structure of an atom from some elementary science. Atom has the central nucleus. Nucleus has protons and neutrons, and the net charge of a nucleus is positive. So that's the nucleus, and nucleus is surrounded by cloud of electrons. Okay, and in a neutral atom, the center of the electron cloud and the nucleus, they overlap each other. So the net charge is 0 in neutral atom. So this is the cloud, electron cloud. So the center of that is also at the nucleus. So the centers overlap, giving net 0. Now there are also atoms that lack either positive charge or that either lack negative charge or that have excessive negative charge. So they are called ions, right? You might have seen this in chemistry. So positive ion is where the number of protons are more than the number of electrons. So an atom loses one or more electrons, resulting in net positive charge. So that's positive ion. And sometimes atoms may gain excessive electrons, resulting in negative ions. So you might have, if you have taken chemistry, you have seen this many times. Sometimes in molecules, there is breaking of bonds between different parts of molecules. And when they break bonds, a part of the molecule carries positive charge with it and a part carries negative charge. So that's how they become charged. Okay. So the one that carries the net negative charge becomes negative molecular ion, and the one that carry net positive becomes positive molecular ion. Okay, so that's the molecule, and there's a breaking of the bond in the molecule. So you might have seen this before. Proton and electron have same charge. The charge in a proton and electron is 1.6 times 10 to the minus 19 coulombs. The only difference is proton is positive and electron is negative. Though their masses are different, proton is much heavier than electron. So that's the mass of protons, 1.67 times 10 to negative 27 kilogram. Electron is 9.11 times 10 to minus 31 kilogram. So there are different ways we can charge substances or objects. One way is by induction. Okay, so for example, let's say we have two neutral objects, in this case metal balls, and the metal balls are touching each other. So let's bring a charged rod near the balls. Okay, so we have this positively charged rod, and when we bring the rod near the metal ball, the charged rod attracts all the negative charge towards it and repel all the positive charges away from it, okay, which we called polarization. So there is polarization of charge. So there is attraction between positive and negative, and there is repulsion between positive and positive. So now if you separate the metal balls, so the positive charge will remain on the one on the right side, and the negative will remain on the one on the left side. And if you move the charged rod away, so they become positively charged and negatively charged. Okay? So this kind of induction, this kind of charging the objects is called induction. So let's see an example. So a rod attracts a positive charged hanging ball. The rod is, what do you think? There is attraction between rod and positive charge. So rod is negative. Think twice, okay, when you answer. That's partially correct. Huh? E? Yes, E is the right answer. Why is E is the right answer? Can you explain? So this could be either this could be either negative, or it could also be neutral. Okay, if it is negative, that's obvious, right? Unlike charges attract. So we learned last time, unlike charges attract, negative attracts positive and positive attracts negative. Now it could also be neutral. So what happens is when you bring the positive charge near a neutral rod, it polarizes the rod. Okay, what that means is it attracts all these negative charges towards it and repel all the positive charges away from it. Okay, now there is this separation of charge, and there is attraction between unlike charges. There's attraction, and there is also repulsion between positive and positive. There's this repulsion. Now we know that the force, attraction and repulsion, it depends on inverse of square of the distance between them. Greater the distance, less is the force. Shorter the distance, more is the force. So there is greater attraction because they are closer. So this is greater. And there is also repulsion, but that's smaller or weaker. So that means attraction wins in this case. Okay, there's both attraction and repulsion, but attraction is much stronger than repulsion. Okay, so let's look at this question. So something is, okay. So these are the things you do with the charged rod, the rod and the metal balls. So you bring the charged rod near the balls, and the charged rod is then removed, and the spheres are separated. A, B, C, D, E, C. Again, think twice when you answer. So they are charged when you bring the rod near the metal balls, and because they are still touching, so when you remove that, move that away, there would be redistribution of the charge because they are still touching. Okay, so this one becomes negatively charged, this one becomes positively charged, and when you move this away, what happens is they are still touching. So now they will redistribute. Okay, some of these will go that side, and so this becomes neutral. So there's redistribution, making them neutral again. Okay, I mean positive charges do not come here, but these negative charges will leave this ball and making it neutral. Okay, this becomes neutral again, and when these these negative charges join this positive charge, that also becomes neutral. Okay, so the right answer is E. Now you may be thinking about this one, so let's look at this question. When you answer the previous question, you may be thinking about this one. Okay, so now it's C. So you make it negative, this becomes positive. Okay, you separate, you then you without moving this away, you separate the metal balls, and then you move that away. Okay, you move that away. Now the charge remains in this ball and that ball. So 1 is negative and 2 is positive. Okay. So there are two types of materials. One is insulator and the other one is conductor. So the outermost electrons are what we call valence electrons. So in case of insulators, valence electrons are tightly bound because the outer shells are full, so they are tightly bound. So that means they cannot move in the material. Whereas in the metals, because the outer shells are not completely full, so the valence electrons are free to move. So they can move freely in the material. That's why metals are a good conductor of both heat and electricity, because electrons can transfer the energy or charge. Whereas in insulator, electrons cannot transfer the energy or they cannot transfer the charge. So it's bad conductor of both electricity and heat. So this is very important term that you need for many fields like biology, chemistry, physics. Dipole. So dipole it's a charge distribution that has two different charges of same amount separated by small distance. So you have bunch of positive charges, 3 positive charges here, and 3 negative charges, so equal amount of charge, but they are separated by some distance. So when you have two charges, two opposite charges, okay, net positive and net negative, separated by some distance, this configuration is called dipole. Okay. You can create the dipole by polarizing the atom. So you have an atom here. In neutral case, like I said before, here in neutral atom here, so the center of the negative charge and the center of the positive charge overlap. Okay, so the center of this is at the center here, and the center of the positive is also exactly at the same location, so they overlap. But if you bring a external positive charge near the neutral atom, the positive charge, this external positive charge, attracts all the negative charge towards it and repel all the positive charges away from it. So that's how you can create a dipole through the polarization. Okay. So that's what this picture shows. So when you bring an external charge here, it attracts the negative charge. This is the attraction, and there is repulsion here. So some molecules need external force to make them dipole, but there are some molecules that have permanent dipole, okay, without applying external force. They naturally have dipole moment, dipole, they are dipole. Like water is a dipole. How water is dipole? So there are hydrogen atoms. Hydrogen atoms have net positive, okay, so these two hydrogen atoms have net positive charge, which we represent by this delta. And this oxygen has what we call lone pairs, right? So they have lone pairs that makes this oxygen atom negatively charged. Okay, there is net positive charge towards the hydrogen, and there is this net negative charge in the oxygen. So that means there is this net positive charge and net negative charge, and there is some separation between that. So that makes water a dipole. Okay, so H2O is a dipole. It's a permanent dipole. You don't need to bring an external charge or apply some force to create the dipole in water. It's naturally a dipole. And this has lots of significance in chemistry and biology. So the reason water is highly soluble is because of this property, because it has this net dipole. We use the term dipole moment to explain the dipole, the property of dipole. Dipole moment is basically denoted by P. It's the basically product of one of the charges. So you have delta, let's say you have two charges, let's say positive Q and negative Q, okay? So they have same magnitude. The dipole has two charges, but the magnitude of the charges is same, okay? And the distance is d. So dipole moment is magnitude of one of the charges, Q, and the separation distance, d, okay? That's dipole moment. So water can easily connect to different molecules, different other molecules, or with the water molecules, molecules themselves. So this oxygen is negatively charged, net negative, and it can bind with the neighboring hydrogen molecule or hydrogen atom, because hydrogen is positively charged, that is negatively charged, so they can bind each other, forming something called hydrogen bond. So this is hydrogen bond. Okay, so you have hydrogen bond here, hydrogen bond here, hydrogen bond here. So hydrogen bonds are formed by binding this positively charged hydrogen atom with the negatively charged oxygen atom. Okay. It has lots of significance in biology. For example, in DNA, there are 4 base pairs, right? You guys, if you have taken biology, you know that very well. So we have TACG, or guanine, cytosine, thymine, and adenine. So guanine, so in this case also, it's basically the bond between oxygen and hydrogen. Okay, this bond is what we call hydrogen bond. Hydrogen, because this is negatively charged, this is positively charged, so there is always bonding between oxygen and hydrogen in hydrogen bonds. So cytosine has 2 bonds, okay, 2 hydrogen bonds. No, actually 3 hydrogen bonds, sorry. So it has bond here, Okay, bond here. So this one is actually, there's also bonding between, this is hydrogen, this oxygen. Okay, there is hydrogen bond here. There's also bond between hydrogen and, in this case, nitrogen. There is bond between oxygen and hydrogen. Okay, so there are three hydrogen bonds. And in case of thymine and adenine, there are two bonds, two hydrogen bonds between hydrogen and nitrogen, and oxygen and hydrogen. Okay, and this is the region only you can form the pair between G and C and T and A. Okay, so the pairs only form between G, C, and Ta because of this bond formation. Okay, DNA is a negative molecule. It has net negative charge. So a piece of DNA has net negative charge. And we can use that property to do lots of biomolecular manipulations, like cutting the DNA or unzipping the DNA and then executing the polymerase chain reaction. So something we often do in molecular biology is gel electrophoresis, because DNA is negatively charged. So when you apply electric field is where there is positive charge on one side and negative charge on other side. Okay, if you apply this kind of positive on one side and negative on other side, because DNA is, you have a DNA in this whale. Okay, you have a bunch of whales here, so you make a DNA solution, mix DNA with some kind of buffer, and then put the DNA in these whales. This is a gel. Okay, some kind of gel. Okay, polymer gel. So you make tiny holes here, and then you put the DNA solution in that, and you apply that electric field. So when you apply the electric field means, again, positive on this side and negative on this side. So because it's negative, it will be pushed by the negative charges, and it would be attracted by the positive charges. So the DNA molecules migrate from right to left. Okay, and the rate at which DNA molecules migrate depends on its mass. Okay, molecular mass. If you have a bigger DNA, it will be slower than the lighter DNA. So the lighter DNA will move faster. So these are the lighter DNA, and the heavier DNA will move slower. Okay, and then you will have some kind of reference here. Okay, so you have some reference DNA whose molecular mass is known, or whose base pairs are known, and you can compare this DNA with the reference DNA, and you will know the size of the DNA. Okay. You can also do that for RNA. Okay. So this property comes from the fact that, this applicability comes from the fact that DNA is negatively charged. Okay. So you can see the role of hydrogen bond. Hydrogen bond is basically, it's the bonding due to the charge, okay, net charge of hydrogen and oxygen, which makes the polymerase chain reaction, PCR reaction, possible. So you have a piece of RNA. Okay, it has some genetic code, like coronavirus has some genetic code which has, I think, 30 kilobase. I think its size is 30 kilobase. So this coronavirus has 30 base pairs like this. Okay, so this is one base pair. So it has it's RNA, so it doesn't have double strand. So DNA has double strand like this. It has one strand with all these ones and the other strand with that. Okay, so it's stranded like that. So it forms a strand like that, DNA. But RNA has only one strand. Okay, so it has different base pairs, not pair, base. So coronavirus has 30,000 base. These base molecules. Okay, it's the simplest one, I think, 30,000. And in polymerase chain reaction, what you do is you basically make solution of that, okay, and then you add primers. Primers are the separate bases. You have like C, T, A, G. So you have these separate primers, and then you mix that, and then you run through some thermal cycle, and then these will go to this pair, and then they combine, and then they form a copy of that, and then you separate that, and then you make millions of copies of the RNA from one copy. I won't go in detail about that. You will learn that in biology if you take biology course. But again, the applicability of that comes from the fact that these pairs are charged. Okay, they have this oxygen and nitrogen and hydrogen. They have net charges. Okay, so now let's talk about another very important concept called electric field. So we know that when we bring a negative charge towards a positive charge, so let's say here A is positive charge and B is negative charge, they attract each other. Okay, they attract each other. Or if you bring a positive charge near a positive charge, they repel each other. But how they attract each other or how they repel each other, okay, it's not well understood until the beginning of 19th century. So they proposed this model called field model. So what happens is when you have a charge, when you put a charge in space, it alters the space, okay? It alters the space around it. And if you bring another charge within that space, that charge feels the influence of the alteration. So this alters the field around it, space around it. And when you bring that near within the field, it feels the influence of that altered field. Okay. And in mathematical sense, we can say that so this is a positive charge. Okay, when you bring a small charge near that, this charge feels a force due to the, let's call this source charge, okay, main charge, or we can also call this source charge. And this is, let's call that a test charge, okay? These small, tiny black dots are, let's call them test charge, because we want to know how much this positive charge can affect these charges at different locations. That's why we want to call this test charge. We want to just test its strength, okay? We want to test its strength. That's why we call this test charge. And usually test charges are small positive charge. So at different locations, these test charges feel different amounts of charge, different amounts of force. Okay, so it'll feel more force, stronger force near the positive charge. If you put the test charge here, you see this, the force is longer. This arrow means it's feeling stronger force. If you put it here, the force would be, I don't know why it's making this line. The force would be a little bit weaker than here. If you go farther away here, it's even weaker. Okay, so closer the test charge, stronger is the force exerted by this source charge. Okay, and farther the test charge, weaker is the force felt by the test charge. So mathematically, we define a term called electric field. So electric field is force felt by a test charge due to a source charge. Okay. So if you collect all these different forces in the space, it forms something called electric field. Okay. So all these arrows comprise so-called electric field. It's nothing but it's just showing that how much force the test charge feels at all these different locations. So you have, what happened? So let's say you have a bunch of points here, 1, 2, 3, okay, 4, 5, 6, like that. So what are the different forces the test charge feel at that point, at those points, okay? So these are the directions along which a test charge will tend to move due to this positive source charge. Now, instead of positive source charge, if you have a negative source charge, okay? So I have a negative source charge. What happened? Then these test charge, because usually test charge is positive charge. Why? I don't know why it's acting weird. So instead of, again, positive charge, if we have negative charge, these charges are usually positive, small, tiny positive charges. They will be attracted, okay, by the source charge. And because they are unlike charges, this is positive and that's negative, unlike charges, they attract. So these charges tend to move towards the negative. And that arrow, those arrows show the direction along which the test charge tends to move. And the size of the arrow, if you see the size, closer the test charge, longer is the arrow. Farther the test charge, shorter is the arrow. Okay? So the arrows also show the strength of the attraction. So mathematically, we can write electric field as force per unit charge. So whenever you have force per unit charge or something per unit something, how do you express that. Let's say you have a density. Density is mass per unit volume. How do you write that mathematically? Per unit something. What is happening? Okay, seems like the PowerPoint has trouble. Let's just use that. So that's the source charge, and we have a test charge here. So electric field is the force felt by this test charge at that point. So electric field can be defined as force felt by the test charge. So let's write test charge as Q naught. Okay, and we know that force from Coulomb's law, if you guys remember Coulomb's law, force between any two charge. So we have two charges here, charge 1, charge 2. Force is given by K times charge 1, charge 2 over distance between the two charges. Let's say distance is R or D. Okay? So D squared. So in this case, one of the charges is test charge. So 2 is test charge, and we write Q naught for the test charge. Okay, so that's the force. If I plug that in here, so I have K, force is K, Q1, Q naught over D squared, and I have this Q naught also for the electric field. So if I put that here, Q naught, this comes from force, and that Q naught is force per unit charge, which is the electric field. So Q naught and Q naught cancel. What is left is E is K Q1 over D squared. Okay. So this is electric field. So that's just the magnitude. Okay. And its direction is based on this fact. If it is positive charge, its direction is away from the positive charge. So that's the direction of electric field for positive charge. If it is negative charge, its direction is pointing into the negative charge. So that's the direction of electric field of a negative charge. And again, the meaning of these lines or with the arrows is they show which way a test charge will feel the force, or you can also say tend to move. If you place a test charge here, which way it tends to move? So that is shown by this arrow. It tends to move along this line. If you put it here, test charge, it tends to move that way because that's the way along which it feels the force. No, it's not absolute. We also need to consider the direction here. That's a very good question. We also need to state the direction here, but I'm not showing the direction here. So we can just say, if it is depending on what your charge is, you will have to mention the direction here. If it is positive, then it will be that, and then you need to say away from the charge. Okay, direction is away from charge. If it is negative, you need to say electric field is that, and then it's towards the charge. So that's how you mention the duration. So when we calculate the electric field, we don't need to worry about the signs because we didn't determine the sign by using this notion. Okay, let's see how we calculate the electric field. If you take a look at your worksheet questions, it's asking to find electric field of a charge configuration. I don't know the number, but so in one of your problems, you have 3 charges on the corner of a square. So you have a square you have a charge here, charge here, charge here. Okay. What's the value of the charge? Let's look at the question. So this computer is acting funny today. It's not allowing me to type. So that's the question. So there are 3 charges on the 3 corners of a square, and you need to find the electric field at this corner, okay, the 4th corner. So how do we find that? Okay, see if I can download this. Where is that? Desktop. Okay, here is our question. So what we do is we first need to see the electric field due to the individual ones at that point. Okay, so whenever you are asked to find the electric field at that point, imagine that there is a test charge here. Okay, although you don't see any charge here, but imagine there is a test charge sitting there. So test charge is always positive. So imagine there is a small positive charge acting, sitting there. So which way will be the force on the test charge due to this negative charge? What's the direction of the force? It will attract, right? So this would be the direction. Okay, so that's due to E1, electric field due to E1, Q1. So this tends to attract that. And then this one will also tend to attract that. So it will be pointing up. Okay, so that's electric field due to that charge at that point. So that's, let's call that E2. How about this one? This tends to repel the test charge away from it. So that would be the direction. Okay, I'm drawing this thick line here to show you the direction. So that's E3. So this test charge will feel three types of force. Force due to this one, force due to this one, and force due to that one. Okay? So that's, you need to find individually, and then you do the vector sum. So we'll do that next time. Okay? Sorry that I went 2 minutes over the time.